Guys eventually learned that I like response. Thank you. Alrighty. First of all, any questions or concerns? Well, good. All right. Second of all, we ended with Joseph helping us out throwing an egg. And it was a good throw. Right in the middle of the sheet, nice and hard, like I wanted. And when it hit the sheet, it didn't break. But the egg exerted a force on the sheet. The sheet then exerted a force on the holder's hands, and they weren't prepared for him to throw it that hard, I guess. And they let go, which was fine. I'm washing the sheet as we speak, probably. Took it home. And then it came down within the egg in the sheet and hit the ground. Then it broke. So, lessons that we can learn from that are what? You tell the class. You guys learned nothing from it? Well, maybe I'll just write a question on the test then about it. Okay, then. Next. I've been, now that things have settled down and everybody's had a chance to correct their information regarding clickers and responseware, instead of 3/4 of the class not syncing up, I have it down to just half a dozen here. Let's start with again, everybody that's contacted me, your device is working. I'm getting responses with that match to the device ID number. I'm having trouble matching up the device ID numbers with the correct person. That's what I've been dealing with. But don't worry, your clickers are working. If you have these device ID numbers, you need to contact me, please. I'm getting responses for them, but I don't know who they belong to. Also, if you are here, and I assume everybody won't be, so I'll have to send an email out, and forgive if I mispronounce your name, Mahmoud, Al-Mahmoud, Condra Cook, Sean Curtis, Rachel Garby, I'm going to go for it, Juanui Guo, Hayden Harris, Stevie Moon, Courtney Thomas, Ho Ming Zhang. If any of you are here, raise your hand. 1. Well, I might explain why I don't have responses to most of them. What's your device ID number? This one? Great. Which one of the... Sean Curtis is this one. Okay, well, I can fix that. Well, one more down. Good. All right. I was rather surprised, though, how many of you, because I could see behind the scene, entered your first name as your last name as your first name, misspelled your name, put in your wrong university ID number, put it in the wrong format. Many of you have changed your settings in Canvas, so your name is blah, 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 and all that shows up is Lily Who, with no ID number. This has caused much to the problems. I could see it behind the scenes and link people up, but be aware if you have other classes that are using Canvas and you have funky settings in your name, I would change them. Or if you're using clickers elsewhere, they're going to have the same issue. And if you can't ever get linked up, and they don't realize what I've been figuring out, you won't get credit. Okay. Momentum. Momentum P is inertia in motion. This guide to our thinking. Inertia, that's what the mass measures. And V, the motion. And so if you're at rest, what's your momentum? 0. Remember that, because that'll come in handy. And I didn't do the units last time. What's the standard unit for mass? Correct. I heard kilogram. And the standard unit for velocity? Meters per second. So that's what momentum is measured in, a kilogram meter per second. That's what they, there's no fancy name for that one. When we had force, mass times acceleration, that one was the kilogram for mass. And acceleration was meters per second squared. And that one is called a Newton. Momentum doesn't have some funky short name. Sorry. But you should be aware of the units. We did change of momentum. What's another name for change of momentum? Impulse. Good. A lot of people think there's two different things, so when I'm asking questions in the homework or on the test, they get confused. Those are the same thing. If you know one, you know the other. Another way to find impulse is, who remembers? I heard it was, I think, louder. Force times t, you're correct. Very good. Remember that if you want to make an object accelerate, you apply a force to change its motion. Now we're talking about that, how long that force is applied. Because it takes time to apply a force. You can do it quickly or slowly. But the time it takes to apply that force, we call impulse. And that changes the object's momentum. If you know the change in momentum, you got some units or whatever, and you know how long it took to change the momentum, say 5 seconds, could you find the force that was used to make that change? There's the equation. So if you know the change in momentum, and you know how long it took, you would just divide it over, and you would know the force used to bring about that change. Does that make sense? So, back to the egg and the sheet. My emphasis with that was the sheet gives. So when it hits it, the egg hits the sheet. The egg, I can't think of any better word, gives. Recoils a little, goes back. And what does that do? That increases the time of impact. So the force needed to slow the egg down is less. Because you can apply a small force for a larger time to create the same impulse. So you can have a big force over a little time or a little force over a big time. The egg in the sheet was doing this. I want to emphasize, if the egg comes into the sheet, because we did it quickly at the end, it comes in with a certain momentum, mv, correct? It's going yay fast before it hits. So it's, and what's its momentum going to be after the collision? Zero. It comes to rest. The point of the sheet or the wall is to stop it. So yeah, it'll come to rest. V will be 0 after. So before it's mv, after it's 0. The change then is mv. It has a change of momentum of mv. And there's a force required to do that. Whether it hit the sheet or the wall, it would have the same change of momentum. The same impulse required to stop it. Are you with me? One person is. Sure is. I guess it's Friday. Yeah, you guys are bumps on a log. All right. I just fell back. I don't know whether or not you're getting it or not. And silence, all I can take is, okay, I'll move on. Then I feel bad when you miss it on the test. So I'm trying to explain it. All right, so same impulse / change of momentum, whether it hits a sheet or the wall. To do that, you can use a big force if you apply it really fast. That's the wall. Or you can use less force if you stretch out how long the collision takes. This is why we land on pads when we're doing the high jump or pole vault. Or why we have airbags in our car. And if you're not wearing a seatbelt and you run into a wall, what do you keep doing? Moving forward because of your inertia. So you still have momentum. Something has to act on you to change that momentum because you're going to be going at mv, your mass, at some velocity, and you're going to get stopped by the dashboard and the window or the steering wheel. So your change in momentum is going to be the same whether you use an airbag or not. The reason you want an airbag is to extend that collision relatively longer than if you hit the dashboard. Thus, you can feel less force. How does the force, which force is larger? The egg pushing on the sheet, because it makes the sheet fall back, or the sheet back on the egg? They are the same. Very good. Newton's third law. But even though the sheet's moving, are they still the same? Good. Which is larger? That pair? Or if it hits the wall? This pair? Yeah, the wall is. The wall can exert more force on the egg. That's why the egg breaks. The sheet can't. The sheet can't push back on the egg. The egg can't push on the sheet with any more force than it can push on it. That was me hitting the medicine ball on the coffee filter. So these two are the same. These two are the same. But these are not the same. The change in momentum or the impulse is much larger when you hit something hard. Because it can push back with more force, more than you want in that case. Another one that students get confused on. If I jump off the table and hit the ground, what do you think my force of impact is compared to my weight? Same, more, or less? When I hit the force of impact, when I hit the ground, that force between me and the ground is equal to what? My weight, more or less? Who thinks, well, hey, you could do a clicker question. Get some points for this. Pull it out. I'll write the session ID number up here. 353. $353,503. All right. Polling is open. So, force of impact. When I hit the ground, is the force between me and the floor more than my weight, less than my weight, or the same as my weight? Ten, 9, 8, 7, 6, 5, 4. Did I give people enough time to log in? 3. Holler. 2. 1. Okay. Ooh, you're split. More and the same. All right. Let me ask you. When I'm standing here, what's the force between us? You agree that one's equal to my weight? Yeah, the support force. Yeah, you're correct. That's my weight. Okay, just think about it. If you were to lie down right here and I stood on you, you'd feel what force? My weight. Would you like me to jump on you? Why? Because it'll hurt more? And why do you think that is? Because the force of impact will be a lot more than my weight. So the correct answer is more. So a lot of people think just because the object is on something, well, it's not accelerating if I'm just standing there. But if I'm running into you, you got that force of impact. You have to not only apply a force to hold my weight, but to stop my inertia, my momentum. And so you have to apply a larger force. Does that make sense? Good. All right, I got some more conceptual questions to see how we're doing. So let me pull down the screen. I wanted this one. Go. So a lunar vehicle has a certain speed on Earth. If it travels at the same speed on the moon, what's its momentum? How does it compare? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 2/3 of you think it's A. You're correct. Why? Is it the same? Correct. Your mass does not change. Your weight would, but momentum doesn't care about your weight. It cares about mass times velocity. So if your mass is the same and your speed's the same, your momentum's the same. Yes?
I understand why some people might think it would be more mass because of the gravity, the lower gravity up there. But with the mass being the same on Earth as on Earth, that means the momentum is the same.
That's correct. Same result, yes. Another thing, just a little twist on it. Would it be harder to push your vehicle horizontally, make it roll? Say it's in neutral. You're pushing it here on Earth. Move it to the moon. Would it be harder to push on the moon? Would it be easier? Would it be the same? Same. It has the same mass, so it has the same inertia, resistance to change. So you would have to apply the same force to push it horizontally. Now, if you were lifting it, it'd be easier to lift it because you'd be opposing less gravity. But horizontally, same inertia.
So remember, like the Superman number 2, where the bad guy was pushing something on the moon? That doesn't really make a lot of sense.
Superman 2, pushing somebody on the moon. It's been a while since I've watched that, so I'm forgetting the scene. But yes, I got to rewatch that and see, did they abide by the laws of physics or not? And when you bring that up, friendly reminder about your superhero paper. These are the type of things that would be good to employ. And if you haven't read the instructions yet, shame on you, but they're all there. And I say you can create a superpower that goes against the laws of physics. That's fine if you want. You just have to be able to tell me how and why to show me you understand physics. So your superhero can abide by them or not, as long as you explain why. Yeah? On the moon there'd be less friction? Because there's less weight. That's true. That's why I picked a car rolling, because that kind of eliminates the friction between the wheels and the ground. If we were sliding something across, very good. It would be easier because there is a little less friction. Very good. Excellent. All right, polling open. Let's double both the force and the time. What's that do to the impulse? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 61% of you think it's C. Yes. Impulse is force times time. So if you double the force, you double the impulse. If you double the time, you double the impulse. So by doubling both, yes, it's 4 times greater the impulse, quadrupled. Those that got it wrong, does that make more sense? Impulse is based on the force and the time. All right, polling open now. Basically a car hitting a haystack or a wall. Comes to a stop. How does the change in momentum compare? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. It is amazing how well that works. I can just see all the responses go, got to get them in. Most of you think it's C, but a third of you think it's B. All right, somebody that thinks it's B, the stone wall would have a greater change in momentum. Can you explain yourself for us, please? If you're willing. Thank you.
Didn't you say that change in momentum differs according to which force stops it? Like the egg with the sheet? Because when it hit the wall, it's a more hard, it has more force.
Very good. You're remembering back to the egg sheet example. The correct answer is it has the same change in momentum because they come in at mv either way. They stop either way. So the change in momentum is the same, but the force required to do so is greater on the hard surface. Did I say the impulse was greater earlier? If I did, then I misspoke. So, well, I could have said it wrong. We can watch and find out, right? I apologize if I do. It happens. So, getting it clear, the change in momentum should be the same. Do you see why? Change in momentum is the same as impulse, so the impulse is the same. I think maybe that's where I slipped. But the force required to do that is definitely different. Because the wall does it quickly, so it's going to require more force. Where the haystack could do it over a greater period of time, so the force required is less for the same impulse / change in momentum. It's good. Keep me honest. Yes, things are different if the car does not come to a stop, which is why the problem did say coming to a stop. Because in a haystack, if it plowed through, in reality, what's more likely to happen is it would plow through the haystack and not come to stop. Thus, its change in momentum is not as large because the haystack couldn't exert as much force on it. So it was a theoretical problem where it could stop it. Say there's 100 haystacks and eventually it stopped.
Back to the Future.
Yes, Back to the Future did that. That's right. I remember that scene. Okay. The last concept in this chapter is conservation of momentum. And we've already been discussing it. I just want to make it more explicit. Newton's second law helped us get at everything we've just discussed. That you look at how a force changes an object's motion, an impulse changes its momentum. Newton's third law, the third one, helps us get at the conservation of momentum. That fact that if you push on, the egg pushes on the wall pushes back on the egg. They're going to feel the same impulse on each other because it's the same force, right? Newton's third law. And they're the two objects involved in the collision, so that the time of impact is the same. So they're feeling the same force for the same amount of time. So not only does Newton's third law tell us that the forces are equal and opposite when two things collide, but so is the impulse. And with sparing you derivations, we'll just get how we can use that. This is my suggestion of how to solve such problems, conceptually or mathematically. The total momentum before has to equal the total momentum after. So you just look at a collision or a reverse collision. Sometimes things shoot apart, sometimes they come together. Consider everything before the impact happens. Figure out their momentums. Add them all up. That's the total momentum. That has to be conserved. That's what the law of conservation of momentum tells us. So that total is going to be the same afterwards, but they might be going different directions individually. You know, like when balls bounce off each other, or these air carts we're going to do. So momentum total before, total after. So if you had two objects, mass 1 coming in with initial velocity and some other mass, I guess his velocity, So two objects different with different speeds come together and they hit. Then afterwards, one final, two final. You just add up their momentums before and you add up their momentums after. And pay attention to the fact that since velocity is a vector, momentum's a vector, and so if one is moving to the right and the other is moving to the left, they will have different signs when you add them up. Let's do one. I think it'll make more sense. This is an air track. So I got a shop vac behind the wall so we don't have to hear it, and it blows air out of here to help minimize friction so we don't have to worry about friction. And you can see that this has inertia. It wants to just keep going. See, Newton was right, like our hover pucks. Whee! And that'll go for a long time. If I take a second cart with the same mass, and I'm going to let this one come back and hit it, what will happen when it hits it? The total momentum before the collision is this guy will have mv this way. And what's his momentum? 0. So the total momentum of the system before he has it all, mv. What do you think? Well, what must the total be after the collision? mv, right. That could happen a couple ways. These two could bounce off each other, and this one's going twice as fast as this one, so that it still has an mv. Or this one could come to rest, and this one could go with mv. Or maybe they both move this way with half the speed, so that the total is mv. What do you think will happen? All right, let's see. Basically stops. If this thing were more level, it'd be perfect. We can go the other way. Doink. Boink. And so it transfers. Yes, in this case it is because they have the same mass. So here we have mv1 plus mv2 before. But one of them isn't moving. So initially all the momentum is just mv. Afterwards, what happens is final, initial, is this one stops and he leaves. And you can tell, because we just did it, this velocity is the same as that velocity. Because this one has all the momentum initially, she gets it all afterwards. Because they're the same mass. All these masses go away if you divide it out. And so that velocity has to be the same. So let's change the mass. This one's half the mass. This one's lighter. Now we go. What do you think? Are you making a prediction, at least in your head, what's going to happen? Okay, there it goes. Now they do both continue to move that way. This doesn't have enough mass, resistance to change, inertia, to stop him completely. That's like the egg in the bed sheet, so to speak. So this one keeps moving. But it did slow it down a little. Watch this one after the collision, the big one. Compare its speed before and after. Fast, slower. So he's lost some momentum, hasn't he? Where did it go? Into the little one. So this time watch his speed. A little faster. Watch the little guy's speed. It gained momentum. So, if you put numbers in, same formula. Total momentum before has to equal total momentum after. You plug everything in, and you'll know exactly how fast each one's going to be going. In this case, in that example, we still had initial of 0, but afterwards, both had values. This was no longer 0. It still had some momentum, just less, because it transferred some of his individual momentum to hers. What if we went the other way? Let's run the little guy into the big guy. What do you think will happen? Make a prediction in your mind. This guy has more mass, more inertia. Oh, now they go different directions. This one bounces off. But notice his speed. Notice the little guy's speed. It comes in fast, bounces a little slower. It has less momentum because he transferred some of his individual momentum to the big guy, who now moves a little bit that way. Compare the little guy's initial speed to the big guy's final speed. You ready? Little guy comes in fast. Big guy is moving, but not as fast as the little guy because he's got more mass. Well, if you did that one, again, same equations. The law of conservation of momentum is still this. That's the beauty of it. But in that case, we would have, see, we still have an initial, one of them, let's rewrite it. The big one was initially not moving. The little guy was. The big guy then started moving, and the little one bounced off. So this one we have to say is in the opposite direction. Does that make sense? So, and remember in these problems, if you have to solve one, that if you define that way as positive, just be consistent. If you define that way as positive, you'll still get the same answer as long as you're consistent through the problem. You can't change in the middle. Those are called elastic collisions also, elastic, because they bounce off of each other. Like when they hit the ends, they're elastic too. Boink. Boink. Woo. If they stick together, it's inelastic. Inelastic. There's those two types of collisions. And that will become more important with the next chapter when we study energy and how energy is conserved. Momentum is conserved in both. The total momentum is always conserved. So what do you think will happen this time? I'll have that one go. Come, stick to this one. They won't bounce, they'll stick together. Will they both stop? Point which way you think they'll move. Yeah, you see, you guys know that your gut's right. They move together as a system now. This guy still has individual momentum, and so does he, but they're moving together. Notice his initial speed, the first one, compared to how they move after. You see how they slow down when they combine? Initially, he has all the momentum. MV. 0 MV. That's the total. It's all over here. After the collision, they both have momentum. The combined mass, though, is bigger. If the combined mass is bigger, their velocity is less to have the same momentum conserved. That's why they move together with less. What if we use a smaller one? Will they still move to the right, you think? They're going to stick together. an inelastic collision. Yes, they still move to the right, but even slower than before. Wait, was it? I guess it depends on how fast I throw the thing, right? It appears slower to me. That's because this guy initially has less momentum to transfer to the combined system afterwards than this guy. He had more momentum initially. If they're going the same speed, then he'll have more momentum because he's bigger. Good. Let's do this one. I've tied them together so they're held together by a spring. I'm going to burn the string holding it together. So the spring can exert a force on each one. How will the force compare? Your guts were probably right. The same. It's going to push on each the same. Same force for the same amount of time. So the same impulse. Give them the same change in momentum. They're the same mass. So how do you expect their motion to compare after I burn the string? The same. Before I do it, you still can do this the same way. What's the total momentum before the anti-collision, if you will? What's the total momentum before? 0. You still have mv and mv, but they're both not moving. So the total momentum before I burn the string is 0. That means the total momentum after I burn the string has to be 0. But they're going to be moving. It's just one will be moving to the right, one will be moving to the left with the same momentum. If you add them up, one positive, one negative, you'll get a total of 0. Do you see that? Let's try it. It's always good when you get to do a torch anyway. So, yeah, same speed. If I was close to the middle, yeah, they hit the end together, they come back, doink, continue on. How many of you like to hunt or shoot anything? Oh, I'm surprised. Really? Okay. This is my little safe gun. Here's my bullet, little mass. And I'm going to put it in, cock the gun. There's a spring inside. Shove the bullet all the way in. There we go. I'm going to turn on the air track again to eliminate friction, hopefully. And I'm going to burn the string. What do you expect to happen? The bullet will go which way? What will happen to the gun? Most of you are saying it will recoil. You're right. If you've ever shot something, you can feel the force. How will the force compare that the gun exerts on the bullet compared to the bullet on the gun? They're the same. Who will be affected more? The one with smaller mass. Newton's second law. So I expect the bullet to come out faster. Let's see. Not level. Sorry, video guy. All right, back to normal. Okay, that's closer. And sure enough, the bullet went a lot faster, but the gun did recoil. Not much, but it shouldn't. Its mass is huge. So not only from Newton's second law and third law can you figure out the speeds, you can figure out the momentums between them. And again, you would do it the same way. What was the total momentum before the collision? 0, because they weren't moving. Afterwards, they're both moving, but in opposite directions. So if I gave you the masses and you knew how fast one was going, you'd know how fast the other was going. Your book does some examples too. You can go home and take more practice. They like using a big fish swallowing a little fish or something. But that's how this law of conservation of momentum works. And it always works. Even if you're going in circles. We're not going to cover circular motion in this class, but everything we've discussed up till now applies. It's just instead of going in a straight line, you go in a circle. Newton's laws still hold. If something accelerates, there needed to be a force. We have discussed that, remember, if something's not changing speed but going in a circle, the velocity is changing, so there must be an acceleration. It's called centripetal acceleration. There's a force, and everything still applies. And total momentum is always conserved. Something can spin this way, something can spin this way, and the total always adds up. To end, most of you have probably seen a Newton's cradle before. These are the same mass. So just like the carts, if one comes in with momentum mv, it transfers its momentum to his neighbor, and he leaves with mv. And so you can see it come to a stop. It's one of those toys, the clicker clackers. Here's a little version. How many had these as a kid? Okay, I'm not too old yet. All right. That works on the same principle. You can have one go around, and the other one stops at the bottom, knocks the other one around. So they're just transferring momentum from one to the next. Go around, hit it again, retransfer. And that applies. It's because they're the same mass. You can also do it this way. Let's see. Whoop. I did practice. It's big. It's easier with the larger ones, I have to admit. But no. There. If one had more mass than the other, the momentum wouldn't transfer completely individually. And so one would want to move farther than the other, and that'd be really hard. Like this. Here's a big ball and a small ball. So when I lift the small ball, what do you expect? It's like that. The little cart running into the big cart. The little one bounces off. Doesn't transfer all of his momentum over. But some goes to the big ball. He moves, but not as fast as the little ball because he's got more mass. You can see at one point. Follow it with me. It's the second hit, I think. Now. 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 You can see the big ball comes to a stop again. And that's when he transfers his momentum back into the little ball. And you go the other way, of course. Whee! But the fun part, of course, is doing 50 million of them. You know what's going to happen, so let's just do it. So multiple collisions. The simplest way to think of this is the first ball comes in, transfers his momentum to the second ball. He moves, hits the third ball, fourth, fifth, until the one that's free to move swings out with the same momentum as the initial one came in, and they just exchange back and forth. So what happens when you do two? The momentum is now just doubled, right? Twice the mass. So look, two come out because momentum must be conserved. Same momentum in and out. Three. And now it's getting really fun. What if we do four? There aren't four left. If you've played with these, watch what happens. Oh, look, four come out. Because momentum's conserved. Energy's conserved too. That's next chapter next week. The end of this chapter I didn't cover. It won't be on the test. I'll explain it next week. Collisions in multiple directions, in 2 dimensions. It's the same thing. You just have to do them separately. But don't worry about it. You don't need it for the homework due this weekend. So have a good weekend.